Okay, so we just introduced this coordinate v related to time and space x. So we're getting back into flat space-time, and we want to learn. There's going to be a parallel here between what we do here with flat space-time and curved space-time in the Schwarzschild metric. So the flat space-time metric, right? The space-time interval is, if we have the speed of light, c squared dt squared minus dx squared as we had it. Actually, we had c equals 1, but it doesn't matter. Just leave c there because it straightforwardly, we're dealing with light, so we kind of want c to be there. CT, so let's write this. So maybe we can start by pointing out that on an XT diagram, we know that light to the left is all diagonal like this, and light to the right is diagonal like that. And so the light cones are like this, right? They are triangles that point everywhere in the same direction. And we want to look at what happens to these light cones as we change coordinates to this v coordinate. So we will replace the t with v and x. So ct is equal to x minus v. And so we have c dt, which is dx minus dv. And so our ds squared becomes dx minus dv squared minus dx squared, which is dv squared minus 2 dv dx. And if we're thinking of light as we want to, then ds squared is 0. And this becomes dv squared minus 2 dv dx. And so we can do 0 equals dv by dx squared minus 2 dv by dx. And so the solutions here are either dv by dx itself is equal to 0, or we have dv by dx is equal to 2, right? So the solution to this is v equals constant, and the solution to this is v equals 2x plus some constant. And so if we make a diagram and v equals constant, right, so this is a vx diagram, then v equals constant looks like, right, this is a constant value of v, it's a horizontal line. So this represents light going to the left, right, for different values of v, and light going to the right would have this equation. So it's different points along here, right? So the intercept has different values, but it has a slope of 2. So we're talking about lines that are, I don't know, that's a slope of 2. Right, so these are the light paths, light to the right and light to the left. And so the light cone here is sort of stretched, if you will, a little bit. Right, we do the same thing that we did there. We see this. And so there's no real reason to do this for t and x space, it's flat space-time. But the point is that because it doesn't illustrate anything, we just changed coordinates, and so we ended up stretching the light cone such that it's horizontal here, and not quite, it doesn't have the same slope there, but it does have some slope there. The point is that we are in a situation where we're using coordinates t and r in a curved space, and we found that as we approach some value of r, right, the light cone seems to be closing in on itself. And so that looks a little strange. We want to cross this r equals 2gm over c squared. such that the light cone doesn't do that, so we can get some greater physical insight into what's happening, into the physics of that region. And so the idea is, if we can find coordinates, we can parallel this project in TR curved space-time for the Schwarzschild metric, then we have a better chance of understanding the physics if we can sort of stretch the light cone out. And that's where we're headed.